Good afternoon, everybody. I can see quite a few of you have joined, so I'm going to make a start. Firstly, thank you very much for joining us for our presentation today on a drilling engineer's reflections on control of well claims. I'm Hayley, Marketing Executive for Charles Taylor Adjusting, and I'm just going to cover off some quick housekeeping before we start. So firstly, please note that all attendees are muted, so we can't hear you rustling around, don't worry. But if you do have any questions or comments throughout, please type them into the questions box on your side panel, and we will address those at the end. Please also note that the session is being recorded today, and we will send this around to you in the follow-up email. We would be really grateful for any feedback that you may have, and there will be a QR code on the screen at the end. So if you could take a couple of moments for that, that would be great. So to introduce our presenters today, we've got Dr. Yuejin Liu, Senior Engineering Adjuster for Natural Resources in London and Singapore. He joined Charles Taylor Adjusting in 2015 and since then has handled numerous losses involving control of well events, oil spills, well failures, and drilling equipment loss and damage. Prior to that, he spent 33 years working in the oil and gas industry, most recently as technical lead engineer for BP Global Major Projects. We also have Mike McMahon, Managing Director for CTA Natural Resources in London and Singapore. He joined Charles Taylor Adjusting in 2011, and since then he has handled claims arising from many aspects of construction and operation of oil and gas assets. Prior to this, he has spent over 10 years in the marine and construction industries as an engineering project manager. You can download their full bios in the handout section on your side panel, as well as our Global Natural Resources Capability Brochure and profiles of our full London team. So I'll now pass back to Mike to make a start.
Okay, thanks for that, Hayley. Welcome everyone, and thanks for your attendance this afternoon. And thanks to the Insurance Institute of London for giving us this opportunity to talk to everyone this afternoon. We've been asked just to put this slide up at the beginning of the presentation and then also at the end for those of you collecting CPD points. So the learning objectives from this presentation today is the basics of drilling and controlling a hydrocarbon well. We're going to look at some of the sorts of things that can go wrong when drilling a well, and then how policyholders and insurers may have differing views on what may appear to be very simple concepts. So just a couple of quick slides before we get started about Charles Taylor Adjusting. Most of you, I'm sure, will know us, but for those that don't, we're a leading global loss adjusting business primarily focused on resolving larger and complex losses arising from major insured incidents and claims. The business is structured in four effective areas, being aviation, marine, natural resources, and then property casualty, technical and special risks. We, Yuejin and myself, represent natural resources business, where we deal with upstream, downstream oil and gas claims, power, mining, and renewables business also. The organisation has grown an awful lot recently. We're now at over 1,200 adjusters within the company worldwide in 120 locations, 30 countries, and over 6 continents. And on the slide here is just a representation of some of the skill sets that we have within the organisation. I'm not going to read through all those now, but as you just heard from bios, that Yuejin is an expert in drilling and control of hydrocarbon wells. I myself am a marine and mechanical engineer by background, but I've been adjusting for nearly 10 years now. So the presentation is going to take two parts, really, essentially. The first part will be technical in nature, and Yuejin is going to give that and look at the basics of drilling an oil and gas well, and the sorts of issues that might come up when doing so in terms of how to deal with kicks and bringing well back under control. And then in the second part of the presentation, we're going to move on to more insurance matters. We're going to look at, in particular, EED 886. And then Yuejin and I will have a discussion about some examples of well control claims that we've looked at in the past. And then we'll just summarize there with what our approach to investigation is when it comes to dealing with control of well claims. So with that, I'm just going to hand back to Yuejin, or hand to Yuejin rather, who's going to kick us off with the technical matters.
Good afternoon. Thank you, Mike. Thank you, Haley, for the introduction. Thanks everyone in the audience who take time for this webinar. Now, I saw some of you may have been on a drilling course, but some of you maybe not. So I thought it would be useful to start the present before we talk about well control. First, just to refresh your memory, to give a brief overview of how we drill and complete oil gas well. Now, shown on the screen on the right-hand side is a picture. Imagine at the top is a drilling rig in the offshore environment, and towards the bottom is the oil reservoir we try to reach. Now, in between is several thousand meters of rock formation. Now, to start drilling, first step is always to install a pipe called a conductor, which is typically between, say, 20 to 36 inch to a depth of around 50 to 100 meters. Now, conductor is really a structural pipe to isolate the shallow, loose soil and support the weight of the subsequent casings, wellhead, BOP, etc. And once the conductor is installed, we will start to drill the hole section. In this example, is a surface hole using a drill bait and connected to the drilling rig by the drill pipe, joints of a drill pipe, and then we rotate the drill pipe to drill the hole. The surface hole section typically to a depth of around a few hundred meters. And once the surface hole is drilled, we'll run a casing string into the hole. Now, this casing string typically could be 13 threads casing around, and of course, running joint by joint into the well. The surface casing is a pressure containment casing. Basically, it's a pressure seal. And once the casing is running into the hole, and then we're pumping cement around to fill the gap between the pipe casing and the wellbore, basically fill the annular gap. And then we'll install the BOP, blew water preventer stack, on top of the wellhead, on top of the well, for well control or pressure control in the subsequent drilling. And then we'll drill another hole section, typically to another few thousand meters below surface, could be a 12¼ inch in diameter. And then we will run another casing string into the well. In this example, could be intermediate casing or production casing. If it's a production casing, that means the casing will be used as a pressure barrier when the well is on production. And similarly, we're pumping cement around to fill the annular gap between the casing and the wellbore. And then we drill another hole section. In this example, we'll penetrate through the oil reservoir, typically say in a 8½ inch or 6 inch hole in diameter. And then we'll run another casing string into the well. And in this case, the casing only overlaps with the previous casing by, say, around 100 meters. We call the liner. And this liner will set across the reservoir hole section. And then similarly, we're pumping cement around to fill the annular gap between the liner and the wellbore. And that's basically the end of the drilling phase. The next phase is what we call the completion phase. Typically, we'll start the completion by displacing the well to clear water or clear brine. And then we'll run a completion tubing, a tubing string, into the well. And then we don't cement the tubing. Instead, we use the packer, as shown in this example. The packer would seal the annular space between the tubing and the production casing. and the tubing would be used as a conduit for the oil and gas flow from the oil reservoir to surface. And that would be the end of the drilling and the completion. Oh, of course, we have to run a perforating gun to punch holes through the production liner to establish communication between inside the wellbore and the oil reservoir. And to put a well on production. Now, to drill a well, of course, we need a drilling rig. A drilling rig would consist of a number of important component systems. Now, from well control standpoint, mud circulation system is probably one of the most important drilling system. Now, on the left-hand side picture, imagine this is a rig, land rig, showing on a land rig. At surface, we would have mud tanks or mud pits holding several hundred or could be a few thousand barrels of drilling mud. Then we're using mud pumps to pumping this drilling fluid through the surface lines into the top drive and into the well through the inside of the drill pipe, downhole, and then coming out of the drill bit into the annular space between the drill pipe and the casing, and that flew back to surface, and then through the mud shell shaker, etc., and then back into the mud pits. That's a complete mud circulation loop. And of course, when we circulate drilling mud, we'll monitor the mud volumes going into the well and coming out of the well. And why we pumping and circulate the drilling fluid? The most important function, especially from well control standpoint, is basically using the mud hydrostatic in the well to balance the pressure in the formation rocks, and also to prevent the wellbore from collapse, and also to bring the drilled rocks or cuttings back to surface. And of course, there are many other functions as well, but those three would be the most important functions of the drilling fluid. And the most commonly, there are two basic mud systems, oil-based and a water-based drilling mud. Water-based mud is basically the liquid phase consists of 100% water, while oil-based mud is basically 70–80% of oil plus 20–30% of water. Then we add barite into the mud to control the mud weight. Barite is a solid powder material, is very high density, around 4.2 Sg, basically over 4 times heavier than water, to increase the mud density. And then we add the polymer, bentonite, and other chemicals to control the mud properties. Now, when we talk about well control, we often talk about kicks. And what is a kick? A kick is basically the flow of the formation fluid we call the influx into the wellbore in an uncontrolled, unintended manner. Now, if that kick or influx in the wellbore not controlled properly, and that influx may escalate, expand, and then become out of control and become a blowout. Now, how do we detect a kick at surface, when we take an influx downhole? As I mentioned earlier, when we circulate the drilling fluids, we'll measure how much mud going in, how much mud, monitor how much mud coming out. So if we say pumping 500 barrels of mud and downhole, but there are 520 barrels coming back to surface, that means there are 20 extra barrels of fluids coming from downhole, and that could mean a formation influx. So we use the surface tank volume, monitors by surface tank volume, to detect a formation influx. Sometimes we also use a tank called a trip tank, basically a slender, a few feet in diameter, a smaller tank to monitor the volume coming back, which can detect the volume in a 1 or 2 barrels will be more accurate. And also we perform a flow check. Basically, when you stop pumping, the mud would stop in coming back to surface as well. But if the mud still continue coming back to surface, that means we are having downhole influx into the wellbore, and therefore confirmation of formation influx. Now, typically, when we have a formation influx, it could be water or oil or gas. And of course, gas is the most challenging to control because the gas is expandable, is lighter than mud, and it will move up a lot in the wellbore and expand in volume. And therefore, you need a bigger pressure, a higher pressure to control it. And also hydrocarbon gas, it can be easily ignited at surface and causing fire on the rig, etc. And also sometimes we may have H2S gas, which is highly toxic and also may cause equipment damage as well. And most often, when we have an influx, it's often a mixture of oil and gas and even water. Now, what are the causes? How a kick occur? And most often is because the mud hydrostatic in the wellbore is not enough. Basically, your mud density is not sufficient to balance the pressure in the formation. And that's what we call the underbalanced kick. And therefore, you need to increase the mud density, basically, to control the kick, to kill the well. Another important cause of a kick is what we call the swapped kick. Basically, imagine when you try to pull the drill pipe out for changing a drill bit, etc., you're creating some kind of a piston effect, some kind of a suction effect below the drill bit. And you may, if you pull in too fast, you may suck the formation fluids into the wellbore, and that's what we call the swap kick. Also, sometimes the influx can be caused by mud contamination by gas or oil, lightweight fluids. Imagine you drill through a rock, a volume of rock. That rock contains 10–15% of porosity, pore space, and in the pore space contains gas. When you drill through that rock, those gas will come into the mud and then move up the annulus, up the wellbore, would expand and then causing the mud contamination become more and more severe, and causing the invasion, causing the reduction of the mud density, reduction of the mud hydrostatic, and therefore causing the formation influx. Also, sometimes the formation influx can be caused by mud losses or what we call the mud circulation. So when you pumping mud into the well, there's no mud coming back. Instead, all the mud will go into the formation, a weak formation, which because it's so weak will be broken down, and all the mud going into the formation and nothing coming back. And sometimes the losses are so severe, the mud level in the wellbore become to drop, and therefore reduce the mud hydrostatic, and then causing the formation influx. Those are probably the 4 most important causes for causing a drilling kick or well control kick. Now, what do we do when we take a kick? The most important is to shut in the well as fast as you can by stop what you do, stop the normal operation, and close the blue water preventer, the BOP stack. And you do that as fast as you can to minimize the influx volume, because the less volume you take, the easier it is to control the influx. And imagine if you were drilling before taking the influx, and then you have to stop drilling and then turn off the mud pumps, and then you check whether still there's a mud coming back to surface. In the deep water, if it's very critical to close the well quickly, you may not even do this check of a flow and straight going to the next stop to close the annular BOP. That's usually the first BOP we close. We'll talk about BOP in the next slide. And then you pick up the strain to check where is your tool joint, and then close the pipe run. Pipe run is the more reliable high pressure rating BOP. And on a floating rig, we will hang off the drill string on the pipe run. Now, once the well is shut-in, we'll record the surface pressures on the shut-in well. And on the drill pipe side, we'll call the surface pressure as the shut-in drill pipe pressure, SIDPP. And that basically reflects how much underbalance downhole basically is reflect the difference between the mud hydrostatic and the formation. On the annular side is the shut-in casing pressure, and that pressure usually would reflect what type of influx, whether it's gas, or oil, or water, and the volume of the influx. Once we shut in the well, and then we can decide, we can relax a little bit and decide the best way to control the well. Now, BOP stack, that's probably the most important well control equipment on a drilling rig. And the BOP stack usually is a BOP stack. At the top of the BOP stack is the annular preventer. That's the preventer we first close in usually. And the annular preventer can close on a range of pipe or even casing sizes, from say 1 inch or few inches up to 9 5/8, typically for 13 5/8 BOP stack, for example. And also, which allow the drill pipe to pull through the drill tool joint. But annular BOP is more flexible, as you can see. But also downside is the annular BOP would have a lower pressure rating, usually about 70% of the BOP stack rating. For example, if it's a 10,000 PSI BOP stack, the annular preventer usually rated to around 7,000 PSI. And also annular BOP takes slightly longer to close, usually between 30 to 60 seconds. Now below the annulars, there'll be several types of what we call the RAM preventers. Those preventers would have a full pressure rating, so 10K BOP with a 10,000 PSI pressure rating. It's quicker to close, usually less than 30 seconds, and also can support the weight of the drill pipe. Won't allow the tool joint to go through because. And there are fixed runs, showing this picture on the bottom. Hopefully you can see my pro. Basically, fixed run is a fixed size. It's a 5-inch pipe run with a close on the 5-inch drill pipe. There are variable run which can close on a range of drill pipe sizes. Give you a bit of flexibility, but have a low capacity for supporting the drill pipe. And then there are bland shear run, which would cut the drill pipe and close the well completely. If on a deep water drilling rig, well, typically you will also have a casing shearer which can cut the casing, cut the large size casing. And of course, on a BOP stack, we would also have a choke and a kill lines, which would allow the mud circulation for mud to heavy mud, kill mud to go into the hole, and also allow the formation influx to circulate out of the well. Now, once the well is shutting on the influx, the rig personnel would need time to think to make a decision how to perform the well kill operation and make a preparation. Sometimes can take hours or days if you have equipment to have to be mobilized. Now, during this time, the well will be monitored. Imagine, as shown in this picture, the well has been shut in on a gas influx, showing here as a gas bubble. Now, because the gas is lighter, the gas will rise in the annulus towards the surface and expand its volume. So, and that's what we call the gas migration. during the gas migration, we must control the gas migration volume by letting out some of the mud volume at surface to control the gas expansion, so that we can maintain the bottom hole pressure relatively constant. And this, as shown in this example, is at 4,500 psi. And this can be usually done in a simple situation by simply using the shut-in drill pipe pressure, as shown in this example, as a 200 psi. Using this shut-in drill pipe pressure as a pressure gauge, but maintaining as a constant, so that the bottom hole pressure is not too high to break down the formation, or not too low to causing more formation influx. And typically, in a realistic, much more kind of a realistic situation than reality, volumetric control is much more complex, much more complicated, and usually takes hours or even days and even weeks in some situation. So it's much more complex. Now, another well control technique is the circulating kill technique. It's basically we circulate the mud and to bring the formation, to remove the formation influx out of the well, so the choke and the kill lies on the BOP stack. First of this method is the driller's method. Essentially, with this method, we will circulate the well straight away once the well is shut in, as long as you have sufficient mud at surface. Even with the original mud weight not sufficient to kill the well, but you can remove the formation influx in the first circulation. And once you have sufficient volume of increased mud density, and then you can start another circulation to kill the well. The second method of this circulating kill is the engineered method. Basically, what with this method is basically once you shut in the well, you'll record the surface shut-in pressure and decide what's the mud density you need to kill the well, and then you prepare this kill with mud, and then you start circulation to kill the well. In theory, this will kill the well in one circulation. In some cases, would result in less pressure on the wellbore. That's the advantage of it. But in reality, it's often a combination of both. Basically, when you shut in, you want to keep the mud moving by using the driller's method. And in the meantime, you prepare the kill mud. And then once the kill mud is ready, and then you start the engineer's method to kill the well. And of course, with this kill method, there are certain limitations. And as you can imagine, you must have the drill bit at or near the bottom to be able to circulate the kill mud into the well. And also, you must be able to circulate well out of the well without breaking down the formation, causing more complications, more potentially underground blow up. And also, your surface well control equipment must be able to handle the influx with a sufficient pressure rating, for example, equipment pressure rating, or even sufficient capacity with the mud gas separator to handle the gas volume. And in some cases, you must be able to handle the H2S if there's a possibility of H2S in the formation influx. A third well kill technique is the ball heading kill technique. And with this method, basically, you just pumping mud, kill mud into the well through the choke and the kill lines at surface to basically try to push or squeeze the formation influx back into the formation. And of course, you can imagine you must be able to pump the mud as fast as you can, at least to be able to overcome the gas migration velocity in the wellbore. And we use this method sometimes because the drill string, as we mentioned earlier, drill bit is out of the hole or long way from the bottom, so you can't circulate using the circulating kill technique. And also, if you certainly you may break down the formation, and therefore you perform the bore heading kill. Sometimes if you're drilling a very deep hole, the open hole section is fairly short, it's probably only the reservoir hole section. And you know, when you bore heading the formation influx will go back into the reservoir. Or you have the H2S, which could endanger the rig personnel, etc., and then that would be the especially workover, only reservoir is exposed. And then we'll use the bore heading kill technique to kill the well. And of course, there are limitations. Of course, if you have an open hole section 1,000 meters, the open hole will fracture or break down at the weakest point, and that weakest point may not be the formation where you're taking influx. So you could end up in the situation where at one formation you're taking influx, but the other formation you are pumping mud in. So there's a potential risk there. And usually once you perform, bore heading kill, usually it's very difficult to go back into drilling again, and usually would end up to plug, abandon the whole section and perform the sidetrack and then re-drill that whole section. And therefore, bore heading kill is usually the last resort and in the well control techniques. Now I'll hand over back to Mike, who will talk about the policy and some case examples.
Okay, thanks, Yuejin. I think my screen is showing again there. So as Yuejin just made very clear, the whole process of drilling and controlling an oil and gas well is very complicated from a technical point of view. And of course, the principal risks that are associated with drilling an oil and gas well are controlled through technical means, through industry experts, good quality equipment, lots of certification, as we would expect in an industry where the risks are potentially so high. As this image here shows, this is a case we dealt with a few years ago now, but things do go wrong. Things can go wrong. In this occasion here, there's a blowout of a gas well. You can probably make out in the middle of the picture there. There's the gas well is blowing out, and what's left of the rig is just showing above the surface of the water. And in circumstances like this, insurance has a role to play in the overall sort of risk profile. And I'm sure many of you will be fully aware that there's a sort of a generic form of insurance called control of well insurance, sometimes called operator's extra expense. But for the purposes of this discussion now, we're going to focus on EED 886, which is a form of policy which was developed by the Joint Rig Committee at Lloyd's back in 1986. It's still in regular use today. Certainly we see it come up time and again in the cases we deal with. So we're going to just focus on that wording for the purpose of this illustration. I don't propose to go into the construction of the wording in any great detail, other than just to show really here that it's split out into three sections, being sections A for control of well, B for redrill and extra expense, and C for seepage and pollution cleanup and contamination. There are also a number of endorsements that are available to buy by the insured. Some of these here: care, custody, control, underground control of well, making well safe, and an extended redrill. And of course, the form of policy that the insured decides to buy is very much dependent on the risks as they see them. But for the purposes of today, we're going to focus on control of well, section A, and really what we're really looking at is to get Yuejin's view on when a well is out of control and when it's not, because that's really the key question in all control of well insurance. Clearly, the picture on the slide here, the well is out of control. That's probably not for debate, but it's not necessarily always as obvious and straightforward as this. And the other one I highlight here is underground control of well. Of course, the underground control of well claims can be very complex for us to deal with as well, because unlike the image shown here again, there isn't an awful lot to look at, and therefore it becomes a much more complicated to ascertain whether actually the well is out of control underground. So we're going to look at, here we go, right, okay, yeah, so you look at the wording for ED 886, and I'm just showing these extracts here. I'm just taking a moment to read it. So the coverage is to reimburse the assured for actual costs and expenses incurred by the assured in regaining or attempting to regain control of any and well which gets out of control. So again, as I said before, that key term there is out of control. When is it out of control? Well, helpfully, 886 gives us a definition, which again I'll just read. Well is out of control when there is an unintended flow from the well of drilling fluid, oil, gas, or water above the surface of the ground or water bottom, which flow cannot promptly be stopped by use of equipment on site and/or blowout preventer, storm chokes, and other equipment required by the due diligence or warranties clauses herein. And the reason I highlight promptly and stopped is they're really key words in these clauses, that, because to my mind at least, they're quite subjective, and certainly when you start applying the facts of a case to these, that tends to be where we have a lot of our discussions about what does promptly mean and what does stopped mean, and we'll have a look at that in some of the examples we're going to be looking at shortly. So conceptually, it's very simple, and I'm going to try and make it as simple as possible. When we're dealing with cases on this, we have to satisfy insurers that these three things have been satisfied really at its simplest level. So has there been an unintended flow from downhole above the ground? Is it true that the flow could not be promptly stopped using the equipment on site? And have the conditions of the warranty and due diligence clauses been met? But we're going to look at those clauses very, very shortly, but it's a really important part of controller well insurance to make sure that indeed the warranties have been met, and also the requirements of the due diligence clause and the policy have been met. But a real key to this is that, again, coming back to that question, is the well out of control? And if those first two questions are satisfied, then yes, the well would be out of control, but both need to be satisfied. So as I said, I'll just put these up on the screen. I'm not proposing to read through them. We're a little bit tight on time already, and I want to get to these examples that we're looking at. But needless to say, that it's important to ensure that everything has been done right, that the right equipment's on site, the right personnel are on site, the right certifications on site, and the right procedures are being followed all through the process of drilling or producing from a well. So controller well insurance isn't necessarily, or claims arising from controller well isn't necessarily different to any other type of loss that we deal with. It's really important for an adjuster to obviously establish all the key facts very, very early on, or as early as we can. But all claims tend to follow a similar process, and it's these three steps really. So again, back to those basic questions, we really distill it down to its simplest form. Has there been an unintended flow from downhole above the ground? Could the flow be promptly stopped using the equipment on site? And has there been a breach of the warranty and due diligence clauses? So just looking at each of those very quickly, what we need to ascertain or satisfy insurers that there has been a well that's been flowing to the surface. We need to check that the pressures in the well, what the pressures in the well are rather, with the BOP shut. And then if indeed the well is flowing and there's and the pressures are unstable, then we need to ascertain that the influx that's in the well needs to be removed. And Yuejin's just talked about some of those processes that are used to do that. And the three that he's just explained would be referred to generically, I suppose, as conventional well control techniques. They're obviously not what you want to be doing on a day-to-day basis, but they do happen, and the drillers are well prepared for them. And those things, again, just volumetric kill, circulating kill, bullheading. So from an insurance point of view, by and large, we would suggest that the well is not out of control simply by the fact that those conventional well control techniques have been employed. What's more likely are some of these specialist techniques haven't been applied, such as firefighting, well capping, the need to drill a relief well, which we're going to look at in a short while. And then again, back to the warranty and due diligence, it's really a case of reviewing what paperwork was in place on site, what certification was on site, and then checking that off against the technical and regulatory requirements. And very often that comes down to a judgment as well, when there's any sort of subjectivity in the process, when there's any sort of performance setting standards rather than prescriptive standards. So that's very much a technical thing that the likes of Yuejin spends a lot of his time trying to work through. So we're just going to look at these three examples now, and I think Yuejin, if you can come back and join us, if that's possible.
Okay.
Yeah. So I'm just going to run through these all these examples here are very loosely based on things that we've actually dealt with in practice before, but a lot of the details have been removed just to make it simple for illustration purposes, really, and to allow us to focus on the key question is the well out of control, and hopefully you'll find this useful as we go through these examples. So I'm just going to highlight the key facts here. So in this instance, we're drilling with what's referred to as MPD technique. We haven't explained that so far, and I don't propose to do so now, but it's a fairly specialist drilling technique. There's been a washout in the drill string, which is quite simply a hole in the drill string, which, as Yuejin explained before, being able to control pressures down the in the well bore is key to being able to keep the well under control. So if you lose any piece of equipment which is instrumental in doing that, then you run the risk of something going wrong and taking a kick. So here that has happened. We've taken a kick. We've got fluid coming up to surface, but we know that the flow can be controlled using the BOP at all times. So in this instance, we're going to talk about the annular BOP, which Yuejin described earlier, which is effectively a sort of rubber ring which closes around the drill string and stops flow coming up through the annulus of the well bore. All the pressures in the well are being managed by bleeding off, so as and when the pressures rise, they can be bled off and then reduced back, and then they'll come back again, or may come back again as they're bled off, and the BOP is shut again, or the choke line is shut again. But this situation escalates for us, as you were hearing earlier. One of the key functions of drilling mud is actually to circulate through the well, and one of the functions it does is to carry drill cuttings, so the rock that's been drilled out up to the surface, so it can be disposed of. So if you lose circulation, you lose the ability to do that, and there's a potential, especially with a well like this, which is shown as being horizontal, that the drill cuttings will settle down into the bottom of the well and cause the string to become stuck. Sometimes you'll be able to pull that out using the rig equipment, just haul it out, and other times that can't be done. So in this example, it can't be done. The drill string needs to be severed. We've lost the ability to circulate through the drill string, obviously, so there's been necessary to bullhead the well by pumping heavy mud into it, and then abandon the open hole. Ultimately, there's no way of drilling through where there's an existing drill string stuck, and we've had to kick off a sidetrack and re-drill the well that way, and claims brought for the costs of dealing with the incident. So if we just apply our tests, our key questions again. So has there been an unintended flow from downhole to above the ground? Well, yes, there has. That flow we heard about, that's effectively a kick that's come up to surface. The next test is it true that the flow could not be promptly stopped using the equipment on site? So Yuejin, are you there, or have you gone again?
Yes.
Yeah. So I mean, what's your view on that? So what we're talking about, the BOP being shut in on the annular.
Yeah.
Is that stopping the flow, or is it not?
Yes, it did. The BOP, annular BOP, and the RAM preventers both working okay. Both working properly. So even during the kill operation, when you perform kill, you may circulate influx out, but that flow is intended flow. But at any moment, if there's unintended flow coming back to surface, we can simply close the annular BOP or RAM BOP to stop the flow, and therefore the flow can be promptly stopped.
Yeah. Yeah, I think tend to agree. But what can cause an example like this to be a bit more contentious and where a lot of discussion can come is notwithstanding the fact that the flow has promptly stopped, it's still been a pretty bad day for the drilling contractor in that they've spent a lot of time, possibly days or weeks, as Yuejin described earlier, controlling the well. Of course, the rigs are very expensive on a day basis. They've lost tools downhole. They've had to plug and abandon the hole and re-drill the well. And yet, unless those tests have been satisfied, then the coverage all sort of flows from that test as to whether the well was out of control or not. But yeah, I would agree that that doesn't seem like it was out of control as the policy intends. This second example is an onshore blowout, very different set of circumstances. It's a shut-in gas production well, very old, 40 years old. Maintenance records, as you might expect over that period of time, have been lost. With a shut-in well, you wouldn't expect it to start leaking, of course, but in this instance, it clearly has. The gas is ignited, which is what we see in the second image on the right-hand side. And although there's nothing on site to help control a situation like this, obviously the wellhead is just on its own in the field, but equipment has been brought and tried to bullhead it. As Yuejin says, that's normally a fairly effective way of bringing the well under control, but also a last resort. So again, just looking at our tests, has there been a flow above the ground, an unintended flow? Well, clearly there has. And is it true that the flow could not be promptly stopped using the equipment on site? Well, again, that's obviously the case. This image on the right here, and it's a fairly agricultural picture of a JCB effectively, but if you can see my cursor, I hope you can, just at the bottom of it here, at the bottom of the bucket, it's got a stinger attached to it, which is effectively a pipe, which has been poked into the wellhead. And what they're attempting to do here is pump brine, so fairly dense water with salt in it, into the wellhead in order to perform a bullheading. Now, I think just I'm going to pass on to Yuejin. I mean, ordinarily you would expect to be able to bullhead with something more substantial than brine. I suspect you use something heavier if brine isn't successful, which it hasn't been here.
Yes, if the downhole, I mean, this is a very old well. If it's say the casing and tubing still have the pressure seal, pressure containment integrity, usually bullheading would kill the well, basically. But I think in this case, because for whatever the reason, we could not, could not be sure, 100% sure, but for 40 years old well, could be a chlorine, could be whatever the other reasons, the casing lost its pressure containment integrity. And when they perform the bullheading kill, it started leaking into the outside casing. So they have to, in this case, they have to stop the bullheading. They could not bullheading from other annulus because that might fracture the formation outside the casing and causing underground flow, underground blowout. And that can be even worse, even we basically that would mean a total loss of control of the operation.
Yeah. Okay. Well, I think so the due diligence becomes relevant for two reasons. Something like that, I suppose, is for the initial event. Why did it get out of control? We need to explore that and understand why it happened, how it was allowed to go undetected. But also there's a secondary point there that if the well isn't in very good condition, or at least the condition of it is not well known, then it can lead to a huge escalation in costs, because bullheading, as you can see there with JCB and a stinger, might not be a very expensive operation, but the picture at the bottom here is actually showing what did need to happen. And we can just see on the right here, this is the well that's blowing out. On the left here is a piling rig getting about and putting in the surface casing in preparation for drilling a relief well. And what happened here over the period of 6, 7, 8 months, there was a relief well drilled to a depth of about 3,500 meters to intercept the original well, which was the only way to actually bring it under control. Yuejin just mentioned there that it's also a risk that you cause an underground blowout by fracturing the formation downhole if you try and pressurize it too much from the surface. This next slide is actually got a video. I hope it's going to come through okay, and the quality of it is good. But it's not the same. It's not the same case. It's a different case. But this is where there was a failure downhole. And I think, Yuejin, will you just talk through some of the key points as I put it up?
All right. Yeah. I think that's the probably initial phase of the fire over the rig, over the workover rig. This is example workover rig. Yeah, burned down the workover rig. You know, basically the workover rig falling into a crater, and all the drilling equipment. You can see the gas seeping through the formation, come back to surface all around the well side, causing fire.
Yeah, so not just up through the wellbore, it's actually come up through
Not just
the Earth's
well, yeah.
surface. Yeah.
So that's the original wellbore. The gas is still coming out.
And the rig's been lost down there. We can make out some of the. Yeah, I think that it's going to zoom in a minute. We can make out where some of the original pad from the rig was. Yeah. Oops, sorry.
So that's probably.
Oh, it's gone the wrong way. Apologies. Oh. Oh, it's gone. Apologies for that. I think I may get away with the surprise there.
Yeah. Methane gas is much more kind of polluting to the atmosphere than CO2, I suppose. So they burn the methane gas. Yeah. So you can see as well, safety reason as well.
Yeah, yeah. Okay. That was a fairly extreme example of an underground flow, but there's also we often see cases where there's things going on downhole that can't be seen. And as I said at the head of all this, there's also an endorsement for underground control of well. So the ED 86 wording is almost identical to that for surface flow, with the exception that it actually talks about unintended subsurface flow of oil, gas, water, and/or other fluid from one subsurface zone to another subsurface zone via the bore of the well. Which, unless controlled, prevents continuation of any operations. So we're just going to look at an example of that. I'm a bit short on time, I'm being told, so I'm just going to go straight to the example. But it's essentially the same test as for the surface flow, but there needs to be subsurface flow. So in this example here, we've got a well that's being drilled. Quite simply, the pressures at surface become erratic. There are mud losses and gains experienced over many days, much as Yuejin described earlier on. The downhole conditions become unpredictable, and drilling becomes very problematic and potentially hazardous. So decisions taken to plug and abandon the open hole and re-drill via a sidetrack. And then the claim comes on the basis that there's been an underground flow. A claim is made for lost time, plug-in abandonment, and re-drill. So what we're talking about here, there's an influx zone. So there's a high pressure zone in the drilled well. It comes up into the formation, but rather than coming to surface where it can be dealt with, it goes into what's called a lost zone or thief zone, where the formation pressures are lower than those at the bottom. Allowing for to be a cross flow from one zone into the other. So Yuejin, I'm just going to ask these questions again. I mean, it's notoriously difficult to ascertain whether there's been an underground flow or not, but do you want to just tell us some of the techniques that are available to determine that?
Okay, Mike. Underground flow. Yeah, usually if you have underground flow and everything happens below surface, so you can't see, you can't hear, no, you really don't know what's happening. So it's very hard to determine whether there is indeed underground flow downhole. So we have to use kind of special techniques, but there are to detect a certain signs, and the most typical sign is the shutting pressure, as we talked about earlier. Shutting casing pressure fluctuation is not stable, that kind of thing. You know, we can use the mark logging data to detect the fluctuations. We can also detect the shutting drill pipe pressure, etc., to make a judgment whether there is indeed some underground flow. But of course, if the underground flow would broach into surface like we saw in the video earlier, and that's easy, yeah. We know there's underground flow, or in the offshore environment, oil coming out into the sea causing pollution, and then we know there's an underground flow. But in most cases, I think in most cases, certainly in all experience, is the underground flow is usually just being contained downhole, and it's very difficult. You have to use a specialized technique to be able to determine that.
And is there much you can do about it though, other than just abandoning the well? There's not really much you can do from surface.
Underground flow usually quite hard. It's not easy to control, but it takes time consuming. We didn't have time to talk about the techniques, but usually you can. There are certain techniques, but not guaranteed. And if you usually bore heading, whatever you controlled or not, usually would have ended up to basically abandon the whole section, because once you have underground flow, that means you have a very weak formation. You have a high pressure formation, very weak formation, and it's very, very difficult to go ahead to drill again. So usually you ended up to abandon the well anyway. So usually the plug the well and then re-drill the whole section. That's usually the outcome, basically.
Okay, all right, good stuff. Thanks, Yuejin. I'm being told there haven't been any questions come through yet on the chat. So if anybody does have any questions, then don't feel free to pop them in. We're just about to move on to the last slide now. Even if we don't get around to answering them here and now, we can certainly get back to you afterwards. But I'll just move on to this final slide now and just summarize what we've been through. So the wordings are open to interpretation, but understanding of whether the well is out of control as defined in the applicable policy is absolutely key. Everything, excuse the pun, but everything sort of flows from there. And that's really key to determine that first thing. And often it can be quite controversial, especially if, as we were speaking about before, we have a discussion about whether it's been promptly stopped or whether it's in fact been stopped at all. Very often there's a heavy reliance on interpretation of evidence and also on professional judgment, which is why it's key, obviously, to have specialists involved in making these judgments. Of course, as with any claim, really, capture and preservation of well site data is essential for a thorough investigation and establishment of all the facts. Hopefully you've got a sense from what we've been through today that the control of well in particular is very, very technical in nature and requires real sort of specialist knowledge from the likes of people like Yuejin, who have spent a very large part of their careers doing this stuff. And on a similar note, they must have real good up-to-date knowledge of industry standards, as is really essential for the interpretation of whether the due diligence and also to the same extent the warranty clauses have actually been met in the policy. So I'm conscious that was a lot of information in a relatively short period of time, but hopefully to summarize those learning objectives again, the basics of drilling and controlling a hydrocarbon well, which we went through in the first 20-25 minutes. We've given a flavor of the sorts of things that can go wrong when drilling a well, and also hopefully highlighted a few of the key sort of touch points where policyholders and insurers may have differing views on what might appear to be simple concepts. And that brings us to the end. As Hayley said at the beginning of this, if you want to scan that QR code, I believe it'll take you to oh, I lost it. That's it. I believe it'll take you to a survey, which the feedback will go back to the IIL, and I'm sure they'll refer that back to us as well. So that's everything from us. I'm looking at the panel. I don't know, Hayley, whether there's any questions come through yet. I can't actually see them myself directly if there have, but
no questions. A couple of nice comments. Someone asking for the copy of the slides. Yeah, we can send that as well.
yeah, sure. How do we do that? Do we just put it
We
onto
can send
the...
it in the follow-up email.
Right.
Yeah,
Okay.
so we can send that around. No worries.
Great. All right. Well, if that's all, obviously it was a very strange set of circumstances, but thanks, Yuejin, very much for your participation. Thanks, Haley, for organising this, and also, of course, to everyone for listening in. I hope you have a good rest of week.